This video is part 5 of Chapter 2, Neuroscience for PSY 110S, the Psychological Sciences. We're going to continue looking at the organization of the brain, specifically the cortex, and now we're going to look at what's referred to as the association cortex. The association cortex involves about 70% of the square footage of the cortex. Because so much of what we do in our mental processing is drawing associations, making connections. So when we are engaged in what you could call higher level processing, you're making choices. Think of the example of you sit down at a restaurant that you've never been to before. You have to read the menu, think about yourself, what your preferences are, do you have food allergies? Are there foods you just hate? Are there foods you particularly love? That information is stored in your cortex as part of your personal memory. You're going to incorporate that into your perusal of the menu. You're going to look for certain words. If you're a particularly adventurous person, you'll look for those things on that menu that you've never seen before, that you're really curious about. You're going to do all of that work that includes reasoning, perception, speech, language, and memory, and then pull all those associations together to make decisions. This higher level processing requires the integration of a bunch of different kinds of information. So, using the restaurant example, yourself, the foods you've liked, the foods you've hated, your own particular taste. Do you like spicy? Do you not like spicy? Whatever. Do you have religious or personal choices about foods that you will or will not eat? Those sorts of things are about your personal story. Then you have, elements of information about what things are healthy, what things are not healthy, what just sounds good for today. Is it your birthday? You might then decide to get dessert. So, all of that processing involves a lot of integration of various kinds of information that you need to put together in a way that makes sense. Language is probably the ability that humans have that has generated the most discussion of how different humans are from various other species. Now, we are limited in being able to make the argument that humans are the only species that uses language. That's likely inaccurate, but it's very difficult for us to determine the language abilities of other species because we're so sort of locked into the way we use language and the way we process language and the way language works in the brain. What we know about language processing is that it's a highly integrated process. Broca's area is one area in the brain that's located in the left frontal lobe on the left side. It's responsible for the production of speech. You notice that it's always surprised me that it appears to be such a small area for doing such a complicated thing. Producing fluent speech requires an incredible amount of coordination of the tongue, the mouth, the throat, your breathing. All of those things have to be managed, and then the shape of sounds and letters and words, the cadence, all of those things are more brain related, and the Broca's area really allows us to fluently produce language. It also is tied to our ability to sing and to use words or sounds in those other ways. Any kind of damage to that space, to Broca's area, for instance, if you have an injury to that side of the brain or a stroke that causes damage in Broca's area, it will interfere with or stop the ability to fluently speak. At the same time, you'll still understand what you hear as language. Wernicke's area is in the left, it's in the temporal lobe. It's responsible for making sense of speech and for reading. So you can see the difference here. If a person has a relatively isolated injury to Broca's area, it's going to affect the production of speech, but your ability to perceive and understand it will be unaffected. Damage or injury to Wernicke's area is likely to interfere with the ability to comprehend what you're hearing as speech, and it will interfere with reading, which is one of those things that requires a great deal of integrated activity. Now, a lot's been made of specialization of the hemispheres, and some of it is controversial, some of it is not. There are some aspects of hemispheric specialization that are fairly clear-cut and understandable, other aspects that are not. So one of the things that we do know is that in terms of vision, light waves come from the left visual field and go to the right half of each eye, and then later connecting with the right hemisphere of the brain, and vice versa. So light waves from the right visual field go to the left half of each eye and connect with the left hemisphere. So part of what's going on here is a bit of redundancy, so that you have, the ability to perceive in a way that produces an image that has depth and dimensions. So it integrates your eyes. Each of your eyes has its own physical viewpoint. By having a left visual field in each eye, you then integrate that with the right visual field, the left half of each eye. And then the crossing and interweaving of that information produces what we know of as what we see with two eyes. So in pathways, there are pathways for processing information from both of those visual fields. Half of the fibers from each eye are going to cross over what's called the optic chiasm, and then go to the opposite hemisphere. The right half in the left eye is going to go to the right side. The left half in the right eye is going to go to the left side, and so on. So your authors provide you with this visual of how information is going to cross over, so that what you see in the left visual field, and there are setups experimentally where you can isolate the images of either, say, a cup, as in this graphic, or a group of grapes, which is on the right visual field. And you can then ask questions and then document, where in the brain activity is occurring to process that information. Now, here I have a couple of videos. Apologies. My allergies this year are really bad. Here I have a couple of videos of so-called split-brained people. Basically, these are individuals who, for a variety of reasons, mostly because of severe epilepsy, have had the nerve fibers in the corpus callosum severed, so that it will decrease their seizure activity. So I'm going to show you the first video, and then I'll talk about it a little bit.
We began our journey into the human brain here on the campus of Dartmouth College in New Hampshire. I'd come to meet one of the world's leading brain scientists, Mike Gazzaniga, and a man he's worked with for over a decade. A man with two brains.
You've been working a long time with Dr. Gazzaniga?
14 or 15 years.
It doesn't seem like that long, does it?
The collaboration began when Joe had surgery. And you had this procedure to correct an epileptic problem,
Yes.
is that right?
Trying to stop the seizures. I was having seizures like every day or so, or sometimes 2 or 3 a day.
To control Joe's epileptic seizures, a surgeon severed the connection between the two halves of his brain. Cutting the corpus callosum like this prevented the spread of the electric storms that caused his seizures. But it also prevented the left and right halves of his brain from communicating with each other. In the years since the operation, Joe's epilepsy has been under control. He now earns a living at an egg farm, and in his everyday life, he's largely unaffected by the fact that his left and his right brains work independently. Do you feel any different when you think about something than you did any differently from the way you felt before the procedure?
Just got a backup brain, that's all.
That's something everybody could use, right? I found out how true that was right away when I was asked to draw a different shape with each hand. In a brain like mine, roughly speaking normal, at least all in one piece, the left half of my brain controls the right side of my body, while the right brain controls the left side.
Oh, no.
But because the two halves are connected,
Nothing wrong with that.
getting each hand to work independently isn't easy.
Well, we're seeing the fact that Alan's hemispheres are connected, and that the motor messages from one are confusing the motor messages in the other.
I was just drawing an upside-down duck.
Okay.
But when Joe is given the same task, his two hands operate as if controlled by two separate brains. What's happening is that each half of Joe's brain is given a separate instruction. He's asked to fix his eyes on the cross in the center of the screen. Anything flashed to the right of the cross goes only to his left hemisphere. Things to the left go to his right hemisphere. Because the two don't communicate, each hand does only what its half of the brain sees.
Wow. It's really like two different people doing the same.
That's right. That's the idea.
Okay, Joe, I want you to keep your hands up.
In an experiment that's now a classic in brain research, Mike Gazzaniga over 30 years ago used a similar setup to find out if the two halves of the brain are specialized to do different things.
Ship.
Joe is being flashed a word only to one half of his brain. Words flashed to the right
Storm.
are seen only by his left brain, and Joe can report seeing those words just fine.
Piano.
Good.
But when a word is flashed to his right brain,
Didn't see that.
Okay. Joe, I'm going to ask you
but now watch what happens.
to draw that with your left hand.
They got me lost.
Why don't you try drawing another picture of it over here if that'll help you.
All full.
Oh, okay.
Grr.
It's almost as though somebody has given him a secret communication.
That's right.
Now he knows that it's a telephone. Up until then, he was blind.
Exactly.
When Gazzaniga first did this experiment, it instantly proved that the ability to speak resides almost exclusively in the left hemisphere. Not until he sees what his right brain is drawing is Joe able to name it.
He said church then, after looking at the picture.
But he had to figure it out about as long as we did. That's really interesting. It's a picture here of somebody communicating almost with another person.
The communication is not occurring inside the head, it's occurring out on the piece of paper.
Yeah.
Bob. I really don't know.
You want to draw a little bit more?
So far, Joe has been seeing only one word.
Cat. That's a cat
Things get
sound.
even stranger when he's flashed two words, each to only one half of his brain.
The right hemisphere saw toad.
Yeah.
And so his left hand draws a toad.
So there's the toad.
Oh, it's a toad. And this time I was able to guess what was coming.
Now
We'll put a little three-legged stool in there later or what?
Joe's speaking left brain saw a stool. Saying the word lets the hand that's controlled by his right brain in on the secret. That's great. That's really interesting. And if he had seen that with the corpus callosum intact, he would have drawn a toadstool.
Right.
not a toad and a stool.
Right, exactly the point. I've been doing this for 35 years. Yeah.
And it
Gets me every time.
Yeah, it must. This time, instead of naming the word, I want you to point to the word.
Again, Joe sees two words simultaneously. Bell goes to his non-speaking right brain. Music to his speaking left brain. When asked to point to a picture of what he saw, he chooses Bell. But when asked why,
Yeah, why'd you pick that one?
Music.
and when asked to explain,
It was music, bell, and it was a few minutes ago. Last time I heard any music was coming from the bells out here, banging away.
So the bell's outside here.
So, good enough answer to me.
what's extraordinary is that Joe's speaking left brain concocts a plausible story of why he pointed to Bell, even when some of the other pictures more obviously represent music. Gazzaniga believes this determination to find cause and effect, this desire to explain, is the left hemisphere's most marvelous property.
One of the unique things of the human brain is this need to interpret why two events occurred. What was the antecedent of this? What caused this? And if you can imagine that a species like us that has that little chip in its brain that asks those questions is going to survive rather well, because it's going to figure out more about the nature of the world than a species that doesn't have it.
Okay, Joe, I want you to keep your hand.
But as I was about to discover, the right brain has a very useful survival skill all its own.
Figure. What do you think will happen here?
So for you, we're doing a live experiment. Never done it before.
The experiment involves the 16th century Italian painter Arcimboldo, who made faces out of fruit, flowers, meat, even books. From other research, there's reason to believe that the ability to recognize faces is located exclusively in the right hemisphere. So Mike wondered if Arcimboldo's paintings would look different to each of Joe's two brains.
So will his left hemisphere say, I saw a potato, I didn't see a face? And will his right hemisphere say, I saw the face, and not comment on the fact it was made out of a potato?
You're going to see a figure followed by a choice of two words.
If this works, it'll be terrific, but we'll see. So here it is, live.
Okay?
The first painting goes to the right hemisphere. And Joe points to face.
Down.
The next painting goes to his left brain. And this time he points to fruits. Mike seemed pleased. Are you having a moment?
This is doing good.
Again to the right brain. And Joe sees it as a face.
Point it down.
But to the left brain,
Face made out of books.
Point it out.
Pointed to books.
were you happy with what
Fruit.
you're doing?
It's unbelievable. He's doing it. You see that?
It's good. It's going so fast. You're shifting from left to right so fast. I can't keep up with you. You're used to looking at this.
When you show him a face in the right side, the left hemisphere,
Yeah.
he's focusing in on the elements that made up the face.
Yeah.
When you show him the exact same picture in the left field, or in the right hemisphere, he's focusing on the face and not the elements.
And not the elements. If you came down from another planet and you saw faces and vegetables, you might not think there was much of a difference among them. But the brain seems to be made up in a certain way to say faces are very different from other objects.
That's right.
And one side of the brain specializes in faces.
Exactly right. Exactly right. It is an adaptation that we have to detect upright faces. It's a very important. You can imagine in an evolutionary time that all of a sudden you have the ability to detect quickly an upright face. You want to read the expression on that face. You want to know if it's friend or foe. You want to have a set of questions about that face.
The right brain might be skilled at recognizing faces, but when it comes to what gives the human mind its power, the ability to reason, to invent, to interpret the world around it, Mike Gazzaniga's 30 years of research has taught him which hemisphere he wouldn't want to be without.
The old phrase around our lab is, don't leave home without your left hemisphere. That's where the action is.
So that's a solid description based on Gazzaniga's work with his colleagues. sorry, the video's auto start, that really documents in a pretty stark way what we can learn from this relatively small population of people who have had their corpus callosum split, because it shows us without that integrating force, so cross communication from one hemisphere to the other, you really can show the specialization areas of the brain. Now, there is a lot of pop culture nonsense out there about supposed left-brained people and supposed right-brained people. In people with an intact corpus callosum, there's little evidence to show that people have a dominant hemisphere. What's more likely is that people have abilities that are cultivated that interact with their personalities and preferences to produce different abilities. Now, that doesn't mean that, say, someone who is very musically or artistically gifted, that they don't have strengths that are unique, that are different from people who don't have those particular gifts. But often what makes that person gifted in music or art is uniquely integrated between the two hemispheres themselves. So what does this tell us about hemispheric specialization? The left hemisphere has stronger responsibilities for language, as well as math and logic. Generally speaking, what we learn from split brain patients is that the left hemisphere tends to be more analytical, and also to looking at things as a whole that have to be broken down then into pieces. We also know something about, hemispheric specialization from people who have sustained brain injuries through, disease, catastrophic injury, or stroke, where there's damage to that side of the brain. So if you have a left hemisphere stroke that is adjacent to language structures, it impacts language in a way that doesn't happen if you had the same level of a stroke on the other side of the brain, even in the same relative location. You wouldn't lose those language skills in quite the same way. On the right hemisphere, you have a lot of the responsibility for spatial perception, so being able to recognize shapeness and spatial relationships. Like one really simple spatial task, not simple necessarily, but a very common spatial skills task that we have to engage in is mentally rotating shapes. So if I showed you a model of a house, and I asked you to imagine rotating the house 90 degrees to the right, and then tell me what the house looks like, you would be able to mentally rotate that object. Or if I showed you an image of a letter and asked you to mentally rotate it 180 degrees and tell me what that shape would look like, you would be able to do that. That's a skill that is more strongly associated with the right hemisphere. Solving problems that are spatial in nature, being able to draw, recognizing faces, all of those tend to be a little more dominant in the right hemisphere. That said, unless you are a person who has had their corpus callosum severed, you're going to be using your whole brain. It is fairly mythological that you would have a person who can, through accident, or even better, there are some of these programs out there that you can run into claiming that they will train you to be able to use your hemispheres on command. Don't buy those claims. We use our whole brain for different purposes, and those purposes allow us to have an integrated sense of how the world works as we perceive it. Where we notice the differences is in terms of, when we have disease or injury, what kind of functions are altered, what kind of things are lost, what kind of things are changed as a result. We're going to shift our focus now to the experience of consciousness, which is, it's for a long time in psychology, historically, the study of consciousness was more philosophical than scientific. This idea of subjecting subjective awareness to your own thinking and emotions was seen as more of a philosophical thing to argue about, as opposed to something that you could study experimentally. But certainly it is a clear aspect of the human experience. We are subjectively aware of our inner processing. So if I asked you right now, tell me what you are thinking about and how it makes you feel, you would be able to reflect back what you were thinking about, like, when is she possibly going to stop talking about boring things? You can also tell me how it makes you feel, maybe bored, irritated, or you may be thinking about just how obnoxious that sound of the voice is coming out of the speakers and other things you might want to do. So you would be aware of your own mind wandering and so on. All of that is a part of consciousness. So when psychologists talk about consciousness, they're referring to internal things as well as external. So what we call metacognition is thinking about your own thoughts and feelings, analyzing those thoughts and feelings and being aware of them. On the external side, you're also aware of the fact that you are perceiving your environment. For example, right now, as I'm sitting here, I'm thinking about how many slides are left in this presentation. And I do that because I can look at my screen and tell just how many, but I'm also noticing off into the edges of my consciousness the sound of my furnace in the next room, because I'm recording in the quietest room in the house, but still there are sounds from the house. All of that is a part of my conscious experience of things like sensory stimuli in the surroundings, things I can hear or feel or see or smell or whatever. I'm also aware of my own thinking, like that internal dialogue of all the other things that I really need to do today, my internal to-do list, or just my thoughts and observations, like, am I hungry, am I not hungry, that sort of thing. Or, is there any coffee left in my mug? I'm really just not sure. All of that's part of conscious experience. So a lot of what's going on in terms of your brain and your body functioning, despite the fact that we are quite aware of many things, a lot of what your brain and your body is doing, you have no conscious awareness of, nor do you need it. Think about the idea that if you had to be consciously aware of your pancreas doing its job, of your gallbladder, of your stomach, of your intestines, of your heart, your lungs, your throat, the back of your ear, if you had to be consciously aware of every single aspect of your brain and body, it would be utterly and completely overwhelming and a huge waste of energy. Most of that stuff can just go on in the background without your awareness and attention. If there's a big change, and it's going to draw your attention, like say you stub your toe and it really hurts, that may be the first moment that entire day you even notice that you have toes. So there's a lot of what goes on that's not at a conscious level. Some things can become conscious at a moment's notice if we need them to. Other things just remain unconscious to us all the time. One of the areas of study that's related to the study of consciousness is the study of sleep. Sleep is one of those things that's an absolute human necessity. We have to have sleep or we decline in function rapidly. When we get at least the minimal amount of sleep, we tend to function better. When we are sleep deprived over time, we suffer major problems. So what do we know about sleep? And your chapter gives you sort of the bare bones. discussion of sleep. You could do a whole semester course on sleep and not even be able to cover the entire topic. Broadly speaking, there are 5 stages in the sleep cycle. And the way they're studied is through the use of an EEG, or an electroencephalogram. Stage 1 is about a 5-minute period of time, and you can see in the green line on the graphic from your textbook, this early stage of sleep is still fairly active. Stage 2 lasts on average 20 minutes and includes what are called sleep spindles, as depicted here on the drawing, where you have bursts of activity, electrical activity in the brain that punctuate sort of the transmission over that 20-minute period of time. In stage 3, and really stage 1 and stage 2, you're still kind of getting to sleep, getting to full sleep as you go forward. Stage 3 is a transitional stage, which is characterized by the emergence of what are called delta waves, which then characterize much more strongly the stage 4 sleep. Stage 4 sleep tends to last about 30 minutes at a time. And during that time, the parasympathetic nervous system is highly, highly active, characterized by lots of delta waves during that period of sleep. Deep sleep is often, described as that period of time where we really need that sleep. When people have sleep disorders, or even if they just drink too much alcohol, it can really interfere with that stage 4 sleep that is really important for restoration of the body. And then finally, you've got rapid eye movement sleep. So this morning I was having a cup of coffee, and the dogs that live with me were all napping, and one of them was having a particularly interesting dream. I'm sure many of you have observed your dogs in their sleep making noises, their tails wagging, whining, their feet moving, all kinds of stuff. And one of the things you can see is their eyes are moving all over the place. Humans do some of the same things. Now, physically, dogs are a bit more active during REM sleep than humans are. Humans tend to be, during REM sleep, relatively paralytic. Other than the eyes moving, we tend not to move a lot in normal sleep during that stage. So the eye movements, eyes moving back and forth, up and down, very characteristic of that stage of sleep. Now the patterns, these 5 stages tend to repeat about every 90 minutes across the night. Now some of you probably have smartwatches that you wear when you're sleeping. It's not clear, exactly how those watches determine what kind and quality of sleep you're having, other than to detect cardiac activity and physical movement of the body during the night. So I wouldn't make any direct correlations between the information that your watch gives you and the information that could be acquired from an EEG. Your smartwatch doesn't have an EEG. That requires, a monitoring device that's connected to the scalp so that you can get the electrical activity through the skull. What we do know about these 90-minute cycles is you can have, over the course of a night of sleep, stages 3 and 4 tend to get shorter with each cycle. REM and stage 2 sleep periods tend to get longer with each cycle. This is probably why people are more likely to remember their dreams later. So toward morning, because they have more opportunity to wake as they are having those dreams, or to wake immediately after them. REM sleep, the REM sleep rebound effect is something that can be seen when you have this jump of increased proportion of REM sleep if you've been deprived of it. So what researchers do here is they have people in a sleep laboratory. They're wired up to an EEG machine, and their sleep cycles are monitored. If they want to deprive someone of REM sleep, what they will do is they'll monitor, and every time they're about to move into that part of the cycle, they'll be awakened. So they have to then return to stage 1, stage 2, stage 3, stage 4, and then be awakened again. So they're deprived of REM sleep, and then they will be allowed to sleep uninterrupted. And what tends to happen is that they will have a much higher amount of REM sleep, kind of to make up for the deficit. What this suggests is that there's some important role of REM sleep, such that when the body is deprived of it, it's going to try and make up for lost time to get that back. So after you pass through the first 4 stages, what tends to happen is people will recycle through stages 3 to 2, and then enter REM sleep. And this completes the first sleep stage cycle. As the cycle is repeated throughout a typical night's sleep, deep sleep stages 3 and 4 get shorter and start to disappear. Stage 2 and REM sleep periods get longer. So you don't necessarily have these 1, 2, 3, 4, 5 progression. Over the course of the night, the order and the length of time that each of those stages lasts will change. Now, what do we know about deprivation of speech? We know that when people are systematically deprived of high-quality sleep, or even just deprived of minutes of sleep, that it can affect cognition, emotion, even behavior, motor skills. So we know that, and you know this too, if you have been deprived of sleep, it's going to mess with your concentration and leave you feeling weak and discombobulated, one of my favorite words. It will also, long term, if you are deprived of sleep over a long period of time, it interferes with your immune system, which can leave you vulnerable to disease. It interferes with motor coordination, and the integration of motor and cognitive skills, and that can make it more likely for you to have accidents. It can also interfere with concentration, judgment, decision-making, all of those things that are an important part of being able to perform as a student. So why do we need sleep? There's lots of theories for why sleep is necessary. One theory is that sleep is required to restore, meaning, when you are awake and active and burning energy, you're doing stuff that creates waste in the brain and the body. You're also, in little ways and sometimes big ways, you're creating injury, tiny little injuries that need to be restored. So one argument is that sleep performs a restorative function for us. We also have theories and research evidence to support the idea that myelin production occurs during sleep. So when we're sleep deprived, that may be one of the reasons why we lose sort of the efficiency of our cognition and our motor skills, is because we haven't been able to restore that myelination to our neurons. There's also a theory, and again, there's some research evidence to support it, that learning is amplified when we use sleep to integrate information. So, for example, researchers know that if people study and study and study and do an all-nighter and just keep studying and then go take a test, they do more poorly than people who study, sleep for several hours, and then take the same test. Those individuals do better. So the theory is that sleep allows for integration of memories and information, allows it to be processed more deeply and more fully. It's not clear how that happens, but that's the argument. And we know from numerous research studies that if you want to do, if you want to perform well after you're attempting to learn new material, study it, and then just take a good long nap, and you will have retained that information and be able to use it more effectively. Sleep is also argued to be adaptive, meaning that when you are awake and interacting with your environment, there's just so much cognitive activity and emotional activity that sleep, that downtime that it produces, is emotionally adaptive. So sometimes you just need to shut it down, and that appears to have a valuable function for us. There's also research suggesting that, as I mentioned before, REM sleep is important to the learning process. So some have argued that, the content of our dreams, just the fact of dreaming all by itself, there's something going on there about memory consolidation, which is a fancy way of saying weaving your new memories into the fabric of what you already know about your life. So, we often dream about little fragments of our day, or information that we're worried about or that we're interested in. Even when you study new material, you'll find little nuggets of that material just start popping up in the weirdest ways in your dreams. What that may suggest is that your memory system is still working, kind of chewing on that new information and putting it with the other relevant pieces of information that connect to it. There are lots of theories of dreaming, and this will be our last topic for this very long chapter. There are lots of theories. Some have more empirical support than others. Sigmund Freud argued that dreams were the secret to figuring out all of people's hidden desires, conflicts, and so on. But his theory has little to no empirical support, mostly because the theories and hypotheses that he proposed simply cannot be tested. So they can't be tested, nor can they be disconfirmed. Another theory, or hypothesis rather, is called the activation synthesis hypothesis. The argument here is that the sleeping brain is trying to make sense of a bunch of random neural stuff. So it's not that your brain actually shuts down. It's not like sleep means that you've completely powered down your computer. Your brain is still active while you're sleeping, doing stuff. It's just you're not consciously aware of it. So what is the brain doing? The activation synthesis hypothesis is that there's just random spiking neural activity, and in dreaming, connections are made between the random things. Some of the work, you may be blipping on an old memory or a new memory or a new thought, but they're all kind of unrelated. The dream landscape will kind of weave them together in nonsensical ways so that they seem to make more sense. Then there's a neurocognitive theory. This looks at the ways in which dreaming has parallels to conscious wakefulness. The argument is that dreams are interpretations of the argument that is made by the activation synthesis hypothesis is just too simple. The neurocognitive theory argues that dreams are ways to create meaning through integrating our waking experiences with one another. And in that dream state of cognition, you're weaving those ideas together in novel ways. This theory also suggests that across the developmental stages, dreaming is different. So you have, different, it's potentially different purposes for dreaming depending on your developmental stage. So, cognition, emotion, as they are reflected in our conscious life, those sorts of experiences may also be parallel in the sleep life, although they may have a different sort of tone to them, different tenor. And that concludes my coverage of Chapter 2.